Hello everyone! Today we're gonna implement the game of Tetris in Python. We're first gonna wrap it in Gym, then make it compliant with the standards required by EzSpark. While browsing the internet, I found a pre-made project of Tetris, written in Python and wrapped in Gym. So today, we're only going to rewrite this environment in a custom environment, making slight changes to make it compliant with the training of EzSpark. And by the way, you can download this Gym Tetris locally using pip. With this command line over here, pip install Gym Tetris. Then you can run this piece of code to see what the environment really does. I have already done this step, and now we just need to copy-paste this piece of code to see what it does as mentioned earlier. So I'm gonna copy and paste it. Now, let's run this piece of code and see what happens. All right, just a moment. Okay, as you can see here, we are just taking some random actions in this Tetris environment. And obviously, as you can see here, everything is printed on the screen. Moving on right now, let's analyze together what this piece of code really does. As we can see from the code in these lines, it basically imports all it needs. Then it initializes the environment in this way, calling the gym_tetris.make function with the environment name that it needs to use. What it does is just a for-cycle 5,000 iterations. And for each iteration, it calls the env.step function that takes a random action from the action space. It just returns the new state, the rewards for the action taken if the game is done or not, meaning is terminated or not, and finally some infos. After that, it just calls the env.render function that will print the game on the screen. And after the 4 cycles, it just closes the environment with the env.close function. Okay, as you can see from this piece of code, there are some standard functions that are already implemented and are the same functions that are required by Easy and also by Gym. We can see those functions in the standards requirements.txt file. Here, we must implement these types of functions. Moving on. From the code that we saw earlier, we didn't really care about what env.close functions do as it returns. But basically, it just closes the environment. Then the env.reset function must return a random initial state, as highlighted here. And the env.step function must return 4 values. What are they? They are the state, the reward, a value that is called done, and that is just a boolean, and an info parameter. The step function takes an action and must return these 4 values. Basically, this state value is just a list of lists or a NumPy array. The reward must be an integer or a float number. The done value is just a boolean, and the info can be anything you want. So, in this standard requirements.txt, we can see that the state must be discrete, and this means that it must be a list or a list of lists or NumPy arrays. Same goes for the action space. The action space must be discrete, and also all the actions must be integers. And the number of actions must be in a range that goes from 0 to n-1. We can test locally if this environment of Tetris already has the action space that is discrete, and it follows these constraints, and if the state space follows them as well. So, we copy-paste this code in the tetris.py file, and then we can just print something on the screen. For example, what we will be printing now is the state and action space. And we're gonna see if this action space is discrete or not. In this case, we're gonna be following this particular sequence of events. We're gonna copy-paste this piece of code, we're gonna use the state, and then we're gonna print it. For confirmation, we're gonna copy-paste the action space, and we're gonna print a sample of this action space, as I'm pointing in the arrow here. Just a moment while I get everything aligned. Almost done. And moving on. We are going to command this piece of code here because we don't need that. And then we're going to run this file again. So we are going to call python tetris.py as seen here. The state seems discrete. Indeed, it's a list of list, meaning it's a tensor. And the action space is discrete. It takes 12 possible actions. In addition, we can conclude that the action space here is just a set of numbers that goes from 0 to 11. Now, what we need to do is just see what is the state dimensions. So, for this tensor, we need to know its dimensions. In this case, we are going to print this shape. Since I saw the state is defined as a NumPy array, so yeah, indeed, we are going to print this shape. So, just a moment while I apply this on screen. Then run again this piece of code. And as you can see here, the state is 240 by 256 by 3. So in this case, it is such a really high dimension, and we must multiply the first number with the second number and then with the third number. For this reason, we are going to create a custom gym environment where we have our own Tetris. Not only will it run this version of Tetris, but that will also have a lower state dimension. So for this particular reason, we're gonna implement our custom gym Tetris environment, and we're gonna run this version of Tetris that has a lower dimension. We need the part of rendering where the pieces move around. This tensor corresponds to the frame of the current state of Tetris. You can see from the video here that this frame is written in RGB mode. The 3 corresponds to the RGB values, and this screen is 240 by 256, meaning every value is written in RGB mode, having 3 different values for each pixel. To create a lower state, we need to extract from these pixels the pixels where the pieces from Tetris move around. From this tensor, I've created my own custom states function. As you can see here, we've created a new state that is no longer a tensor, 240 by 256 by 3, but rather is just a matrix defined as a list, where each value has been set to 0 if the spot is not occupied by any blocks of the pieces of the game. Plus has been set to 1 if is occupied by one of the Tetris blocks. Moving on. So it seems that we have everything here. We have the state that is discrete and has been defined as a list. Then we also have the action space that is discrete, and it takes some numbers as actions, and these actions are numbers that go from 0 to n-1. Then we also have the dot reset function that returns the state. Then we also have the dot state function. It takes an action and returns a state, reward, a boolean, and an info. Then we also have the dot close function. Next, we want to put this Tetris in our custom gym Tetris environment. So we go to gym Tetris, then we go in gym_Tetris, then we go in envs, and we must implement our custom environment afterwards. Conclusively, we can create our own custom Tetris environment where we just redefine the state space from 240 by 256 by 3 to a list or matrix 20 by 10. So again, we move from 240 by 250 by 3 to a matrix of 20 by 10. So to make something like this, we must re-implement the environment in this way. We just create an init function where we initialize the environment. Then we must re-implement all the functions needed. Meaning, we need to re-implement the step function, the reset function, and also the close function. In addition, the step function must return the state, the reward, the boolean that indicates if the game is terminated or not, and some info. This would mean that the step function takes an action, and then what we do in this function is just recalling the env.state function that is of the original Tetris. We take the state and we redefine the state in this way. We only need to call this function that takes the original state, wrap it in a list, creating a new state with a lower dimension, and we need to implement the reset function, as highlighted here. Consequently, we will need to call the env.reset function, which is the reset function from the original Tetris. It returns a state, then rewraps the state with the getNewState function. Here, the getNewState function. That is always this one, and then we return this new state. Next, we implement the close function that just calls the env.close function from the original Tetris. To locally install this environment, we must define the setup.py file. The setup.py file can be seen here, and it looks like this. We need to import the setup tools, and we must call the setup function from setup tools. You will have to name the package that I named GymMyTetris, define the version, and finally define the requirements. In this case, it's Gym and GymTetris. Then, we can define the author email, description, a link, and we must call the setup tool.find packages. We can run this piece of code. You can run pip -e install GymMyTetris to install it locally, or you can just follow what I'm doing now. Python 3.6 -mpip install -e GymMyTetris. This command line depends on what version of Python you are using. In this case, I am using the 3.6 version. So, we can run this command line, and you'll notice how it is installing. Now, we can test it locally. We can create a new file that we are going to call it mytetris.py. Then we can call this piece of code. We can copy-paste this piece of code here. Before that, we can modify this piece of code, changing some lines and naming our custom environment. In this case, what we need to do is just import gym. Then we're going to do something like this, gym.make. Here, we must name our custom environment. Our custom environment would be called as the package name. In this case, gym_mytetris. Gym_mytetris, double dots. The name of your environment that has been defined here in the init.py file. Then we can delete this line. I did create the render function in our custom environment, but I called it render local. Here. So in this case, you are going to call the render local. And also, we can see the state space for our custom environment. So we can run this piece of code. We're going to call the Python mytetris.py. Okay, so you can see here, this is the rendering and this is the current state space. In this case, our state space matches this rendering, but is not a 240 by 256 by 3 tensor values, but is just 20 by 10 list of values. Thank you for watching. See you in the next video.